Hi, in this video we are going to implement the shortest path Dijkstra algorithm together. So let's get started. I'm going to create the classes in advance. We are going to have an app from which we are going to run our application. I'm going to have an algorithm, for example. It is going to store the Dijkstra shortest path algorithm itself. And in order to be able to construct a graph, we will have vertices and we will have edges. Sorry, not edges, but edge. Okay. So vertex is going to contain a name, private string name. This is the label of the given vertex. Then I'm going to store a reference to the neighbors. It is the adjacencies list. Then I'm going to have a boolean whether it's visited or not. To be able to construct the shortest path tree, we have to store references to the previous vertices on the shortest path, of course. Previous vertex or predecessor. And I'm going to have a private double min distance. And as I said earlier in the theoretical video, that we have to initialize this min distance from the source to double that maximum value. Okay. In the constructor, I'm going to get a name, the name of the vertex, so the name is equal to name, and this, that adjacencies list equals the new array list. Okay. Like this. I'm going to have a public void add neighbor edge this that adjacencies list. This is how we add neighbors to a given vertex. Then I'm going to generate getters and setters. For the get adjacencies, the name, the name not, because we are going to override the toString method. And in the toString method, we just return this.name. Okay, so that's all about the vertex class. The edge class is going to store a reference to, we associate a double weight to aid each of the edges, and vertex, start vertex, vertex, target vertex. And I'm going to create a constructor, generate a constructor using fields. Okay, so I will have a weight, I will have a start vertex and a target vertex. I'm going to generate the getters and setters for both of them. And Ctrl-Shift-F to auto format. Okay, so that's all about the edge class. What about the algorithm? As we have talked earlier, I'm going to have a public void compute path, and we have to specify a source vertex. And then we will have another method, the get shortest path too. So it's a public, it's going to return a list of vertices. So get shortest path to, and we have to specify the target vertex. As you remember, in the theoretical video we have discussed that this Dijkstra shortest path algorithm is going to construct something that's called the shortest path tree. And with the help of the shortest path tree, we just have to specify that what's the target vertex, and we can calculate the shortest path accordingly. So first of all, we have to, because the source vertex is the one that we are standing, I mean the starting point, we have to set the minimum distance to 0, because that's the point we are standing. Then we have to create a priority queue, and this priority queue is going to make sure that we hop to the, as you may recall, the Dijkstra's algorithm is a greedy one. So after visiting the neighbors, we have to go to the next one, next already visited neighbor that has the minimum distance from that given node. And that's why we have to use a priority queue, because it uses a heap as a data structure, and we can get the minimum in logarithmic time complexity. So priority queue is equal to new priority queue. And of course I have to add this source vertex to the priority queue. And the algorithm is quite simple, that while this priority queue is not empty, we just have to get the actual vertex, which is equal to the priority queue dot poll. We are going to remove this vertex that has the minimum, because it's it uses a heap as a data structure. So if we call this poll method, it is going to return us the vertex. Oh, sorry. And of course, to be able to use it, I have to implement the comparable interface to allow the priority queue to decide that according to what property it has to calculate the minimum value, according to the names in, for example, alphabetical order, in order the numbers of edges in this list. No, we want to compare two vertices, a vertex, and implements the comparable interface, and we want to specify that what's the other one we want to compare it to. And it's very important, and we just have to return it is a double. Oh no, sorry, integer. Okay, yeah, because this double that compared to is going to return an integer. Okay, so this that min distance, and there's a vertex, the other vertex, and the other vertex that get min distance. So we have to specify this compare method, we have to override it, and now the priority queue knows that the priority queue has to compare the items according to this compared to method, and it's going to compare the minimum distances. So when we call this poll, it is going to return the vertex that has the minimum distance from that given node, for example, from the source vertex. So that's the shortest path. It's going to give us the vertex that has the minimum value. I mean the minimum distance. Yeah. I'm just going to iterate through this vertex, edge, because we have edges. Edge, the actual vertex that get adjacencies list. And I'm just vertex v equals to edge dot get target vertex. I'm going to just for the sake of simplicity, I'm going to get the start vertex, although the start vertex is just this, but I think that the pseudocode is usually used v and use. And of course I have the double weight, which is equal to edge.getWeight. I'm going to create a minimum distance, calculate the minimum distance via the v. We get the target vertex and we calculate the min distance through that vertex. And how do we calculate it? We calculated that u is the actual vertex, or I don't know, I'm going to get rid of this, maybe it is just misunderstanding. The actual vertex that get min distance plus the weight of the actual edge. This is how we calculate the minimum distance via this vertex. And I just have to calculate that if the min distance via v is less than the v that get min distance, then I have to update our priority queue. First of all, I have to remove the v because it has wrong properties. Then I have to set previous vertex, the actual vertex. I have to set the minimum distance to the min distance via v, and then I have to add it again. So that's why I have to do it, because as far as I know, there's no method for updating items in the priority queue. We have to remove it, we have to update the given vertex and have to insert it again. Maybe there's an update method, it doesn't matter, it is the algorithm that's important. Yes, priority queue that add, that's exactly what we are after. Okay. Then I have a list of vertex, the path of the given shortest path. It's going to be a new array list. And then I'm just going to iterate for the vertex is equal to the target vertex. The vertex is not equal to null. The vertex is equal to vertex.get previous vertex. This is how we backtrack our shortest path. Yes, we just add the paths that add the given vertex. We just make a collection because we have to reverse it. Collection. I think that we have to use the collections that reverse on the path and just return the path. And this is how we get the shortest path to the target vertex. So if we run this algorithm, first of all I'm going to create vertex v1 is equal to a new vertex. It's going to be the A. I'm going to have three, just for sake of simplicity, three vertices, A, B, and C. I'm going to have edges, so maybe vertex 1 dot add, what's the v1, sorry, v1 dot add a neighbor, a new edge, and the double weight is going to be 1. The start vertex is v1 and the target vertex is v2. Maybe we could write our algorithm that we don't have to specify the start vertex because we set it like this, so it is straightforward. But anyways, I don't think that the algorithm is the important, not that how we implement it. Okay, so we added an edge. I'm going to add another edge with a huge weight, so that's why we'll be able to calculate that our shortest path algorithm works fine or not. So v2 dot add neighbor, new edge with 1, and v2 dot v3. So if you see that there's a shortest path from A to C, via from A to B, then B to C, because going from A to C is very, very expensive. It is 10. But going from A to B is 1, going from B to C is 1, 1 plus 1 is 2, 2 is less than 10, so that's why if we calculate algorithm, I'm going to instantiate our class, algorithm.compute path, the source vertex is 1, and then I'm going to system out the algorithm that get shortest path to, for example, vertex 3. If I run it, ABC, you see? ABC is the shortest path. If I set the edge weight to 100, then the shortest path will be directly from A to C, and it is working fine. So you can test this algorithm on huge graphs. I have done it already on several graphs. It's working fine. So this is how we implement Dijkstra's algorithm, and this is just the pseudocode. I mean, we have to create a priority queue, then we have to iterate through until this priority queue is not empty, keeps checking whether there's a minimum distance, I mean there's a shorter path, and whenever we just have to update the priority queue. So this is how Dijkstra's algorithm works. Thanks for watching.